Harris, and I'll be here this afternoon introducing people. And our first talk comes from two old friends of mine, Ross Madon and Enrique Inglesier, currently at Engelhard and the University of California, Berkeley. And this talk is entitled Catalytic Reaction Rates in Thermodynamically Non-Ideal Systems, and Ross Madon will be giving the talk.
Thank you, Suzanne. This particular talk was something that Enrique and I have discussed, I think, well over 10 years ago, while we wrote that Exxon. And an opportunity arose last year when we were writing a paper for a journal dedicated to Professor Budar, and then we decided after we wrote the paper in Journal of Molecular Catalysis that perhaps it was a good thing to share and discuss this work over here. So the topic today is going to involve chemical kinetics in non-ideal systems. By that we mean molecules solvated in an environment that is non-ideal, a liquid phase, for example, in gas-solid-liquid reactions, and reacting on surfaces. When we have a situation in which the reactant or the products are solvated by an inert liquid, we know that we should use thermodynamic activity and not concentration. The activity becomes a relevant variable, and when concentrations appear in rate expressions, what the reasons are and why that happens is what we'll discuss today. By inert liquids, I mean those that do not absorb or react on catalytic surfaces, and we will also touch on zeolites that can solvate all species and present a non-ideal environment to the reaction. We will discuss three examples. The first one is an old example, comes way back from my thesis, and that's the cyclohexene hydrogenation to cyclohexane in the liquid phase, and we'll discuss it over platinum and palladium. The next one is a specific case in the Fischer-Tropsch synthesis in which we'll concentrate on the product olefin desorption as a product and reabsorption of that product in a pore that's filled with a liquid paraffin product. This again presents a non-ideal situation because the pore is filled with a liquid, and it will be a gas-solid liquid reaction in which the gas is outside the pore. And in the final example, we will talk about a zeolite in which the paraffin enters the zeolitic chamber, which is again a non-ideal environment, and we'll discuss something that has come about quite a bit, and that's the importance of concentration enhancement in zeolites, and how important is that, and when does that become important. Before we get to the examples, I want to make a few comments in which, again, when rates are always influenced by thermodynamic properties, the chemical potential, the fugacity, and the thermodynamic activity. And it's very important, like I said earlier, that concentrations only appear in ideal systems. The question is, when does a surface detect the liquid? When is the liquid important? It is important when it solvates the relevant adsorbed intermediates and activated complexes in a reaction scheme. Or it holds a physical barrier by preventing a gas-liquid equilibrium by imposing diffusion restrictions. These are the two places when the liquid becomes an important variable in a reaction. And what will we use to guide us? And we're going to use the transition state theory to guide the analysis of kinetics in non-ideal systems. It will allow us to show when the concentration of reactants can be used and when they cannot be used, because really thermodynamic activity is what we should always obtain. Just briefly, the transition state theory is the rate equal to the frequency at which the transition states move over the barrier. The concentration, or the equilibrated concentration of transition states, appears in this expression, not the activity. So for a simple reaction in which a bimolecular reaction, A plus B, which is now equilibrated with the transition state, and this particular symbol is what I'll use for an equilibrium or quasi-equilibrium going to its products, the relevant equation then becomes the frequency factor, which is the Boltzmann constant, the Planck's constant, temperature, which remains constant, the equilibrium constant for the conversion of reactants to an activated complex, with 1 degree missing, the 1 vibration degree missing. But the most important thing, which I'll concentrate on throughout the talk, is this particular part, in which on the top you have the activities of the reactants, and in the denominator you have the activity coefficient of the transition state, which I'll just refer to as gamma double dagger. You will see this particular equation in much more complicated forms as we start plugging things into it, but basically it's this equation, and I don't want you to get confused by all the other paraphernalia that comes along with it, because this is what is the most important part, especially for this talk. Now again, a solvent, as I said before, can influence the rate of a chemical reaction when it perturbs the activated complex of a kinetically relevant step. Now, when is that most plausible? When is that most realistic? Now, the catalytic cycles involve an entry and an exit step, and a very nice discussion has been given recently by Budar and Tamaru, Thales letters. When the kinetically relevant step is either the entry or the exit step, now the transition state along the reaction coordinate is in between a gas phase or a liquid phase system, a liquid phase a molecule, and a surface molecule. If, for example, the relevant step is a surface step, then the inert liquids will not influence the structure or the reactivity of the species, because the bonds on the metals or the oxides are much stronger than the intermolecular interactions in the liquid. So really the entry step and the exit step is where the important issues are. So let's go to our first example. And here I'm talking about the cyclohexene hydrogenation on platinum in the liquid phase. What was observed is that the turnover frequency over a wide variety of solvents changed. The turnover frequency varied quite significantly with the solvent used. However, if we correct it for the solubility of hydrogen in that particular solvent, we then obtained rate constants that were constant. So here, a very interesting phenomenon. It's a liquid phase. We don't have activity, thermodynamic activity, but we have a concentration of hydrogen in the liquid phase. The rate depends on this solubility of hydrogen. Well, why would something like that take place? Briefly, let's look at the mechanism that has been suggested, and I'm not going to go into details. It's a well-known Horiuchi-Polanyi mechanism, and has been well studied by Burwell, Kemble, Budar, and of course Horiuchi and his people at Hokkaido. And for platinum, the kinetically relevant step is this particular step, and it is the entry step. It is the absorption step, it is the entry step. The step above, going from the gas to the liquid to a Fezisov state, are in quasi-equilibrium. The only other unidirectional, non-equilibrated step is the final hydrogen addition to form the alkane. And we put this together, and of course this desorbs. But the important step here is this particular step. So using our transition state theory, and this is the equation I'd shown you before, I'll change it a little bit because it's much better to write this constant in terms of the change of standard free energies, which makes more sense. And let's expand this. We know that, for example, these solvents are not affecting the surface, and what we do is remove that from the equation. It's a constant. But concentrate on the hydrogen, the Fezisov hydrogen, the gamma and the concentration, and of course at the bottom is your transition state activity coefficient. If you plug the liquid phase activity now, because of this particular equilibration, what we obtain is a ratio of gamma H2 in the liquid phase and the gamma double dagger. This is where an important point needs to be made, is that if these would cancel, you would get this particular observation. And the reason they cancel is because in this particular reaction, the transition state looks very much like the hydrogen molecule that's in the solvent. And the solvent solvates the hydrogen in the liquid phase in the transition state to the same extent, and they cancel, and we end up with what is a concentration dependent of the rate, and that's kind of unique in non-ideal systems. Now let's move to palladium and see what the situation is there. Here we have a turnover frequency which is independent of the solvent use, quite different from the platinum case. The rate expression obtained was dependent now on the gas phase concentration of hydrogen, which is the same thing as the liquid phase thermodynamic activity of hydrogen. So now the question comes, why should the same reaction, cyclohexene hydrogenation, on two similar noble metals, platinum and palladium, behave so differently? One was dependent on the concentration in the liquid phase, one is dependent on the activity in the liquid phase, which is what one would have expected. Again, going through the Horiuchi-Polanyi mechanism, we find now that the rate determining step, or the kinetically relevant step, is now the last step, which we've broken down into two steps: the addition of hydrogen to the half-hydrogenated species, giving you the alkane, which then desorbs. The physisorbed hydrogen chemisorbing onto the metal is now equilibrated. Again, going through the transition state approach, what we obtain, and again, it's this particular term that's important, is that we have the activities of the surface species divided by that of the transition state. Now the transition state is in between two surface species. Plugging in the equilibrium constant of these three steps, which are all equilibrated, we obtain this particular ratio and the gas phase concentration. Everything else is independent of the liquid. It's important to know that in this particular case, these two materials, these two species, RH star and your transition state, don't look alike anymore like in the platinum case. Furthermore, they're surface species which are not influenced by the solvent. They do not cancel. They can be moved into the constant, and we end up with what the observation was, that you have the rate proportional to a gas phase concentration or the liquid phase thermodynamic activity. So again, just to summarize, because these are important concepts which we'll use a little bit later, for platinum, the kinetically relevant step was the entry step. For palladium, it was a surface step. In this case, the liquid solvated the hydrogen and the transition state to the same extent, and the activity coefficients canceled. There was no effect of the surface intermediates by the liquid or on the transition state. What was the result? The cancellation of the activity coefficient resulted in a kinetic process that looked like it's being driven by the concentration of dissolved hydrogen, whereas in this case, we have the thermodynamic activity. So two metals, very similar metals, same reaction, and we end up with a completely different driving force. And so when one says solubility is important in liquid phase reactions, one needs to step back, go through this kind of methodology to see whether the activity coefficients cancel of the transition state, whether they're still there, and if so, is solubility really important? Let's go to our next example. And this is just a cartoon that shows schematically the Fischer-Tropsch synthesis, in which CO hydrogen allows the chains to grow. And at some point, one of the chains hydrogenates, the last hydrogen is added to the alkyl chain to give the normal paraffin. But what's in red is what we will discuss today, and that's the formation of the alpha olefin by hydrogen abstraction and the reabsorption of that alpha olefin. This particular secondary reaction is also not something we will discuss today. So let's concentrate only on this red portion. In Fischer-Tropsch synthesis, and we just take a gas-solid-liquid system like in a fixed bed system, the particle, the catalyst particle, is bathed in the products. It's heavy hydrocarbon products, paraffinic products mainly, and the pores are filled with this paraffin liquid. Outside the catalyst is the gas phase. It's almost like a trickle bed reactor at times, in which the products flow out. So we have concentrated what's happening in this particular pore. And the reason it's so important is that though it was very well known since the days of Harrington and Pickler and Itis and other people working Fischer-Tropsch that olefins reabsorb. It wasn't until much later when we found that the extent of reabsorption is amazing. For example, in many cases, you would not form, you'd form 70 to 95% or more of your hydrocarbon chains of C21 plus only because the alpha olefin reabsorbs. And that's very important for this process. And understanding this process of why this alpha olefin absorption takes place, what allows it to take place to this extent is important. Here's a standard Fourier plot in which you can see that the experimental results occur. They're not a single line like the Fourier distribution would allow us to believe. And it is independent, more or less, of the conversion. You're going from 9% to 72% conversion. So you're basically changing the chain termination because of this olefin reabsorption. We look at it a little bit differently, and it's easier to look at it in terms of what we call a termination parameter. Again, it's this red area that we'll concentrate on. But the termination probability is the rate of termination divided by the rate of propagation. And you can sum it up together for the paraffin case, which is this case, and the net termination of olefins. And when you plot that versus carbon number, what you see is that the paraffins are pretty much unchanged with carbon number and with unchanged. And the alpha olefins dramatically decrease because what is happening is that this term is very carbon number dependent and is contributing to this decrease. At the end, you don't even see any alpha olefins. All you see is normal paraffins. So this high extent of reabsorption by larger olefins is extremely important. Why does this take place? How can we improve our catalysts? There were two explanations given for this alpha olefin reabsorption and the increased residence time of alpha olefins in pores. One is what we gave, and that was that in the pores of the catalyst, the paraffinic liquid causes diffusion constraints of the olefins. And as the olefin size increases, the diffusion becomes more and more limiting so that the olefins do not come out of the pores. There are two issues here. It's not only the diffusion constraint, but also the larger olefins reabsorb more readily. The second explanation given was by the Dutch school and others, in which the higher solubility of these olefins and the strong physisorption of large olefins contributed to them staying longer in the pores. So let's just look at that particular part of the Fischer-Tropsch process in which the olefins are formed from the half hydrogenated species. The olefins then desorb to give the physisorbed olefin, and then they go into the liquid phase and the gas phase. This is nothing but the microscopic reverse of the Horiuchi-Polanyi hydrogenation mechanism that you saw for the cyclohexene hydrogenation. It's really just pretty much the same thing. So now in this particular pore, you have this olefin desorbing and reabsorbing with this scheme that we have put together. Now let's look in the first case in which we say the first step is equilibrium, is the rate determining step. And all the other steps, steps 2, 3, and 4 are equilibrated. And let's assume there's no diffusional restrictions. So using this and using our transition state theory approach, we have to get a net rate forward minus back for this particular reaction. Now this is a little complicated, but it's really the same as the kind of the equation that I showed before with the gamma double dagger, over here in the denominator, and all of these terms basically are terms in the activity coefficients to obtain, from equation 1. K overall is related to the free energy change for the overall reaction. Now, this is important because in this particular step, all the species are surface species. The transition state lies along the reaction coordinate between chemisorb species. When that happens, there is no solvation of any of these species, including the transition state, and the liquid phase cannot be kinetically detected. So the solvation by liquid cannot be detected. So the point about olefins being more soluble in paraffinic liquid is not correct if we assume this particular scheme. Now let's make things a little bit more difficult and change and say, okay, let's assume that the first reaction is equilibrated. The second reaction is now the kinetically significant reaction, and then the steps 3 and 4 are equilibrated. When this happens, now you have the possibility of the transition state being affected by the solvent. Again, putting down the same equation that we've used over and over again, we see now, for example, that gamma double dagger is in the denominator, and the transition state, like I said, lies along the reaction coordinate between the adsorbed and the liquid phase. But what is interesting is that when you have higher solvation, when you have a more soluble situation, your concentration goes up. What that means is now your activity coefficient goes down. So when it goes down, it will actually lead to a faster net rate of desorption and not reabsorption. Completely opposite to what people have said. So the better the solvent, or the more soluble the species, the lower is the activity coefficient and the net desorption is favored. You can also think in terms that if you increase the concentration, the equilibrated concentration of transition states, you increase the net, you increase the forward reaction and the back reaction to the same extent. What's going to happen? The net rate is going to increase in the direction favored by thermodynamics, which is your reaction, which is making olefins. So what you're going to end up with is actually more olefins in the liquid rather than the reabsorption. So what I've shown is that the olefin reabsorption due to solubility or physisorption is not relevant in two cases. Either we have when the desorption and adsorption are quasi-equilibrated, or when they're kinetically irrelevant. It's interesting that if you choose this, you would not get the kind of data that we get experimentally. So the only tenable explanation is that the lower diffusivity, the higher reactivity of the large olefins, allows the olefins to stay in the pores. You have a concentration and activity gradient formed in the pores. They stay in the pores and grow. So again, solubility. Using solubility to suggest changes in rates is very confusing and can be wrong a large number of times. Finally, let's talk about zeolites, which differ from those from liquid solvents, because in a zeolite, everything is encapsulated. You can solvate complexes for all the steps, not just the entry and the exit steps. You can solvate the active site in the zeolite. And you can solvate all the steps, all the chemical transformations that are going on. In essence, we believe that the sites with zeolites resemble homogeneous complexes, where the ligands are really the zeolitic framework that can interfere and attract and change the system. Today what I'd like to do is just very briefly go over something that has been observed and discussed, and that's the high concentrations of reactants that exist within zeolite channels and cages. Right from when Rabot noticed that, and Fresat, and later on Derouin discussed that. Is it true that high concentrations of reactants is why the zeolites work so efficiently? And if so, how can we say that concentration is important or thermodynamic activity is important in zeolites? More recently, Haag, Lercher, Lunsford, and Kong have suggested that paraffin cracking rates are dependent on this intrazeolitic enrichment. The data is conflicting in some cases because we don't yet know whether indeed, even though the paraffin enrichment does take place, whether the rate is due to that paraffin enrichment. We'll use the methodology that we've used before on the other examples. And as I said, this is just a suggestion of how one thinks and how one can use this methodology. Now, as I've said, the zeolites solvate molecules and intermediates trapped within this confined structure. and they represent a thermodynamically non-ideal phase. We have an equilibrium between the gas phase and the molecule that's trapped within this particular channel or cage. We have a thermodynamic equilibrium so that the chemical potentials are equal, and we can derive from that the C gas concentration in the gas phase is proportional to the activity inside the zeolite. So now, if the zeolite concentration is enhanced, as people have said, and I've said that before in the Fischer-Tropsch case, the gamma must decrease to compensate. So at the same concentration in the gas phase, you have a higher concentration here, your gamma, your activity coefficient must decrease. So with that in mind, we have to say, do rates depend on the concentration, or do they depend on the thermodynamic activity? So again, just like in the Fischer-Tropsch, we look at two cases, two possibilities. The first, let's assume that the paraffin is absorbed in the zeolite cage or channel, and it reacts directly with the Bronsted site. So here we have an equilibrated step that we showed before, and now PZ reacts directly with the Bronsted site, giving you products being the relevant step. And again, going through our transition state approach, we get this particular equation, where now here we have the activity of PZ, which is your paraffin in the zeolite. This particular coefficient does not cancel in this case, because this is a paraffinic molecule in the cage, and your transition state, as we know now, is a carbenium ion transition state, which is polarized and quite different from the paraffin. So they're not alike. And in such a case, after we substitute for the gas phase equilibrium, what we end up with is an expression in which the rate is directly proportional to the gas phase pressure, or is proportional to the activity in the zeolite. It is not going to be dependent on the higher concentration of the paraffin inside the zeolite. Now, unlike in the liquid phase, all these other terms can be affected by the zeolite. We'll discuss that in a few minutes later. But now let me go to another case to see whether we can change this and under what conditions it changes. And here I've assumed that the paraffin absorbed in the zeolite forms a precursor. And this precursor is formed from the PZ. This precursor could be a conformation change, a physisorption near a Bronsted site, or whatever. But it is something that's happening in the cage to go from the PZ, absorbed into the cage, to a precursor state which then reacts. So here again, in the transition state approach, we have the activity of the precursor state. Using this equilibrium, what we end up with is this particular equation. Now what we can do is that this paraffin in the zeolite and the precursor state both reside within the same local structure in the zeolite. They're both paraffinic, basically, and they're solvated by the zeolite in an identical way. Now this identity holds. Basically, this canceled, and you can substitute. When you substitute that, you end up with a concentration of the paraffin in the zeolite, because you've been able to cancel the activity coefficient. So in this case, you try to find a way, a mechanism, if that's what the mechanism is for that particular reaction, but the activity coefficient cancels, and when that cancels, you end up with a concentration, just like in the platinum cyclohexene case. You end up with a concentration, and the rate is dependent on the concentration. So now, in a zeolite, if we expand this, basically you have a pre-exponential factor. And one of the things I'd like to leave you with is that the pre-exponential factor, which has not been emphasized, people do talk mainly in terms of activation energies, is very, very important. And the appearance of the activity coefficient of the transition state reflects the importance of the zeolitic structure in the transition state. So the transition state is affected differently in a Y zeolite versus a ZSM5 versus a mortonite or whatever. This is going to be affected, and you're going to get differences in different zeolites. This particular ratio then becomes very important, as well as the absorption constant Kr or Krc that I talked about. So the zeolite basically is an acidic medium where all these interactions take place, and that the site is just at one point where the transition state takes place. So I leave you with these three examples, briefly saying that in non-ideal systems, you must use thermodynamic activity unless the solvation allows the cancellation of the activity coefficient of the transition state. This is usually important for the entry and exit reactions on solid reactions. And in homogeneous catalysis, you can cancel a lot of things because there is a solvation effect. Solubility arguments in gas, liquid, solids to explain increases are often incorrect. I showed that in the case of the Fischer-Tropsch synthesis. Zeolites present a unique case of solvation. Again, you must think in terms of phase equilibrium, where you have the gas phase activity and the activity inside the zeolite. And again, only if that gamma, only if that activity coefficient cancels the reactant, will the rate be proportional to the concentration of the zeolites. That's my story.
We can take a question or two, I think. Ross?
Yeah.
I'm wondering if we go back to the case of cyclohexene, platinum, palladium, if you take those cases and you remove the solvent entirely and just do a gas phase reaction, where does the result fall?
The gas phase results, that's Gonzo's work, I believe that the gas phase results were slightly higher than the liquid phase results. For the cyclohexene on platinum case, they were hugely different.
But for palladium, they were...
Yeah. Well, they're about a factor of 2 or so different. Yeah.
I was wondering if you could give any idea of what this precursor state for the reactant molecule might look like in the zeolite. How does it differ from the adsorbent?
Maybe the theoretician can tell us. Well, I put that together as just, the only reason I put that was to say, how can gamma cancel? This was for a paraffin case. If you have different reaction in a zeolite, and if you find that concentration is important, my suggestion is to backtrack and say, okay, using transition state theory, how can I explain that concentration effect? Because really, it should be the activity. And then, if necessary, you would have to come up with those kind of arguments that are either a precursor state exists, or without a precursor state, is the transition state looking very much like the reactant and then cancels too? So either way, somehow it has to cancel. That's really what I'm